Welcome to Book Club. So we're going to continue on chapter 12. We started it because it's a really big chapter. Honestly, chapters 12, 13, and 14 are really kind of the payoff of all this work that we've been doing. And it's interesting because I'm actually now working on this for multiple clients. So during the course of this really long, I think it's been like a year or something we've been working on this. It's gone from theoretical to practical. So I definitely have some opinions. So we started in this chapter looking at basically designing based on what the users need. And now we're in the consume section. So in the consume section, we are presented with this idea of input data ports, like where the data is coming from the data products. The ideas that she starts with are a subset of what she's presenting. She's really two. One, which is events or snapshots, which is kind of the work streams that we're used to from data warehousing. And this just applied to, the world of analytic microservices. So having them stream into this container as a product. And then she goes to talk about the type of coupling. And so she talks about coupling is dependent on the type of data that's coming in. And she suggests that she wants to keep the collaborating operational system sources in their same domain as the products. And my little comment there is this possible? I think that's kind of aspirational because at least in the world that I'm in, I'm finding more and more and more that they're not in the same domain. I'm lucky if they're in the same cloud. So maybe that's, again, reflective of the world that I'm in. I just think that is, it kind of oversimplifies the problem space. And again, maybe that's unique to my view. Does anybody else want to comment there?
Yeah. Two things, just rewinding a little bit, and I took a note of that too, regarding the events and snapshots. Also it's interesting, but there is that tie-in to like kind of event-based design and having like kind of events, snapshots, aggregate root, everything. So there is an alignment there. I don't know if it's directly aligned to the data warehouse, but I kind of wasn't sure which one she was talking about. But anyway, getting back to like what you were saying about the same teams, kind of owning both modalities. Yeah, I think it is somewhat aspirational for a lot of orgs. And I think like that's the sticky part of implementing these architectures, because I don't think it can be successful if it's like a central data team trying to build this architecture at all, ever. But there's like this reluctance and mismatch of skill sets, I think, for a lot of teams to participate in this, right? Like this, the product teams also producing the data. So it really depends on the org. In some organizations it'll work, but in many, especially if they have kind of a traditional, kind of heritage, data warehousing and central data teams, like it's a big hill to climb for sure.
Yeah, what I was thinking of is we might have like a human resources domain, and they'll have several products, because the more I've been diving into this, we have our general human resources, but then we outsource we have an onboarding application that runs through a whole step of approvals. We've got another application does background checks. So I thought we might have several products and they'll talk to each other and they're all within the same domain, but then you got payroll. Well, they're over at fiscal. So that's going to be a cross-domain, issue. Now, Lynn, in a lot of your work, it sounds like a lot of the customers and people you work with, the whole point with research is to share that data with outside entities. So that's, in our organization, we might be a single cloud and even a single tenant. We're really easy, but I think in your nature of work, just by definition, you're going to be dealing with a lot of disparate data sources.
Yeah, and even when I worked in finance, I mean, they were always collecting external for their analysis. I think because I'm in the modeling and scientific analysis side. So it's interesting, you know, again, this is why it's good we have all of us on the call. So it's not just my view. That's kind of the point, you know. So and then she goes on to talk about, she makes an example of it, like it's aligned in its events. It's consuming the events, which is a common pattern. So event driven.
You're not sharing your screen, by the way.
Oh,
if that's by design, that's fine. It's great to talk, but usually you do share your screen.
I'm so sorry. I am so sorry. Thank you for telling me. So yeah, so now I'm on this diagram here on page 220. So she's you know, drawing the data product, and then it's aligned with events, which again, this is not a really new pattern at all. And then she talks about asynchronous event-driven data, really, or change data capture for legacy systems. And this is very reflective of existing data warehouses. And she talks about change data capture being the least desirable way to retrieve data because it exposes the implementation of a database. So in other words,
Plus on that one.
Yeah, it's the coupling. Yeah, I mean, yes, she's correct. But sometimes it's the only available option, right? So
yeah, everybody, you know, like even in my last company where we pursued this largely, you know, there were the, you know, of course, like the event-driven microservices, and then there were people that just wanted to use the Bezium, right? Like, let's just CDC all the data stuff, like whatever, it's all coming. And I'm like, that's not going to solve any problems other than data transport. You know, you're still going to have none of the desirable effects of what we're trying to do, right? So, yeah, that is, I agree. And Debezium was not a very good solution, by the way.
and the modern version of this, the data lake or data swamp, is we will turn on versioning on all buckets on every location forever, because we're thinking about change data capture, even though we will never look at anything but the latest version or latest 2 versions. And it just basically junks up the system and makes everything slower. So it's actually could be worse because there's less pressure because cloud storage is so much cheaper than relational storage. So I've seen it worse now with just turning on bucket versioning.
Yeah, for sure. I think we're going to talk about multimodal. I'm sorry, what was it? Bitemporal comes up in this chapter a lot. So when we get to that, that'll be a good conversation.
Right, exactly. So then, you know, you can have other products, and this is my world, basically. And this little line right here is very easy to draw and very hard to implement, because you have to have all the federated security. And you have to agree first, and then implement, and then test. I thought this was kind of cool. Excuse me. Self as data source. Basically, you're grooming some of the data by doing some processing. And the example that she uses for this is really kind of cool, kind of modern, and it kind of adds the third prong from eventing or batch input data. She uses a machine learning model to do the transformation. And I actually have this use case for some of my medical analysis, where we've got some, you know, input data, and we are actually doing this with machine learning models. We're trying to figure out which models are most effective. So we would have multiple products, if you will, to compare the quality of the output. So this is something that I hadn't done up until recently, but this is becoming more and more part of my world as the volumes of data increase, because the traditional ways of doing this do not scale. And machine learning allows for greater processing capacity. So that's been kind of interesting. So then she talks about the locality of data consumption, for example, where the data is physically located and whether a consuming data product physically copies the data one location to another, or implementation details. I wanted to scream at this book at this point. And you notice what I wrote here affects cost. This is one of the big problems I'm having in the architectures that I'm building, that there is a lack of understanding of the impact of egress costs. And that's where the cloud vendors are really making a lot of money, because of the lack of understanding of egress costs. And so I am kind of fanatical about this because I have seen customers pay tens of thousands of dollars. This is one of the sources of cloud shock bills, basically. And so I went, yeah, no, it's not an implementation detail. It's not. It's really, really, really important in terms of the architecture. And maybe, again, this is reflective of my experience. I don't know if you guys want to add anything here.
I haven't seen, so egress costs, yes. I haven't seen severe cloud shock from duplicating data within my clients in my experience. However, as much as we say storage is cheap, right? As you start having like single data sets that are hundreds of terabytes, like you start looking at your bill and being like, S3 is starting to get expensive, or kind of managing that data in Redshift is definitely very expensive, right? So I think we do sweep that under the rug a lot. We keep saying storage is cheap, but like depending on the company and the data volume and how often that data set is being kind of replicated and copied to another environment, it starts being at least statistically significant. So it is something to be mindful of for sure.
Well, again, my world is individual files are starting to be terabytes.
Yeah.
And so terabytes, if I gave terabytes, I'm happy. My sort of typical world is the data sets are petabytes.
Yeah.
So.
Yeah, most of my world is still in the hundreds of terabytes, which it's challenging when you're talking about dense data that's hundreds of terabytes, but your world is a little tougher.
Scary, I know. So, and that's just showing basically what we've already been talking about. And then talking about ports, and then again, me being fanatical about costs. I literally am working on a project right now where 11 different research institutions will be collaborating, and we need to figure out where to put the data and then where to process the data. And details like, if you place the data in the same physical region as where you compute against the data, there won't be egress charges, even if you have to move it from a bucket to like a persistent disk. They're so important that we're going to enforce them via policies. Because if you don't, and somebody just randomly clicks, well, what the data is in US Central, but I'm going to just go with US East because that's the default for, EC2 instances, then you have egress. And again, these nuances are so important when you're dealing with these humongous volumes of data. And again, this is, my world, which is not everybody's world. But my argument is that I'm kind of the future, because as more and more data is generated, this is going to be everybody's world.
Yeah,
when you deal with 12 different research consumers, are they pulling down the data and consuming it and analyzing it in their own system? Or are you enforcing, saying, I know all 12 of you want access to our data, but you're going to analyze it in our...
So as part of our architecture, that's why I put add estimated costs. We are including in the architecture what we estimate the cost would be if they wanted to pull the data down versus computing. And again, I don't mean to, just continue to go over and over this topic. It just happens to be something I'm currently working on. And I have also had a previous client where they had to add an organizational policy because as the collaborating research organizations just, did what I just said, they computed all over the world. The originating research location was charged the egress costs.
Yeah.
So that made it even worse because the collaborating organizations didn't see the bill.
The consumer doesn't pay that. Yeah.
Right.
Yeah.
Right. And so it's the source of record, and it nearly, broke their budget in 1 year because it just zoomed out of control. So again, it's just, notes from the real world. Okay, so then we go into transformation, which is true. And all data is messy, right? Everything needs to have some sort of transformation. The way I think of this, and I think this is actually really, really important to data mesh, is it's the anti-data pipeline. And I really think there's a lot of value in that because I have suffered from these really complicated data pipelines that are really brittle because they're too complex. They have 50 stages in them, for example, and they, they're all dependent, and it takes, inordinate amounts of time to make changes. So that's like the general concept of microservices, right? Don't have big monolithic applications. And I think that that's sort of the underlying thinking through this transform data, that you have transforms. So one of the things data mesh suggests is that you break the pipelines apart into discrete tasks, which again is super, super hard to do for existing pipelines. Almost impossible in some ways. So it's kind of going to be a blended situation that for new pipelines, you try to build that way. You build little chunks. But for existing, the only way to really approach it is the same way that you would take a monolithic system that's operational and refactor it. You have to split off parts of functionality to microservices. And I think those same paradigms apply to data pipelines. And I think it's pretty significant. I've never really seen this thinking before architecturally. So I don't know if you guys were that impacted by this section, but I was like, oh, I need to design differently.
Yeah, I agree. I think like smaller isolated components that have clean interfaces but between each other is a much better design than that big monolithic Airflow repo with 50 disparate pieces of code chained together with sloppy kind of interfaces for sure. Yeah, no, I'm 100% in. And I think the thing that becomes like culturally different is who does what, right? So the data producers are also ending up with what you'd call transform too, because they talk about the the kind of organizational keys, right? Like if you're going to have a product, you got to resolve. So you're pushing responsibility to different people who then have ownership of it too, which I think is interesting. But if you can do that, then you've got a nice interface that that like, hey, this data that this team is producing is always going to be, right? It's always going to have this contract upheld. But yeah, it definitely has an organizational impact of splitting up the processing, because traditionally this would all be some central data team, right?
Right.
And now we're saying, hey, maybe it's an outcome team because you care about this certain thing and you're going to create a little mini product. And like data producer, oh, you can't just throw the data over the wall. You got to do this little bit of transformation and processing. So it's very interesting.
So I think this is interesting. I would sort of quibble with the implementation here. I think this is the subject matter experts are using either drag and drop interfaces or very simple scripting languages to do transforms, or you've got very complex transforms that need to scale, and those have to be implemented programmatically. And again, this is an actual area that I'm working on right here. I think that this, like, I've never really heard of Flux, so I don't really know what it is. GraphQL is not non-programmatic, in my opinion. It is programmatic. SQL could be argued. And one thing, because it's not a call unless I talk about ChatGPT, now you can use ChatGPT to generate SQL. So I think that's more of a non-programmatic solution, because you can basically just speak English and it'll output pretty high quality SQL. I would argue before that creating high quality SQL is actually a programmatic skill, because I've seen enough bad SQL that, anyway.
Also seen Spark implemented no better than SQL if you ever run on Notebook. That's
Yep.
Yeah, I didn't find that helpful at all. that distinction between the two, to be honest.
Yeah. So then it's talking about extensible and scalable. this comes from microservices, dumb pipes, and smart filters. So a dumb pipe is a Lambda, basically, and a smart filter is some sort of programmatic code that scales. I'm going to show you an example in architecture that I've been working on.
Awesome.
And then again, I love the ML here, because this is literally another problem I'm working on, which is how to scale complex machine learning. So how to take machine learning as an API and to make it a transform effectively. So I'll actually just start showing you this because I think it's interesting. So let's see if I can make it full screen. Maybe not. I don't know. This is good enough. So this is an abstraction of a customer architecture, set of architectures. This happens to be Google Cloud. And basically what I'm showing here is, if you think of each one of these as some kind of data product in a data mesh, and they're purpose-built. So you match the services. Now, mostly I'm going to use files, so I'm going to use cloud storage, but you could use, transactional Cloud SQL if you wanted to. And then sitting on top of that, you have lightweight processing for lightweight jobs. So lightweight transformation, an example is we have to retrieve metadata about image files, which is just like the name and how big it is and stuff like that. So that's a lightweight job. You're not really actually processing the huge file, you're just collecting metadata. And the way we built that was with cloud functions and workflows, which is like Lambda and step functions. And in Azure, it's Azure Functions and Azure Workflow basically will allow you to collect state information about variables and pass it from function to function, string them together. Azure Step. Do you know what it is, Matt?
I don't off the top of my head. I'm drawing a blank on that one.
Yeah, it's a similar concept. So you string functions together. So what's interesting about these primitives, and they're similar across all clouds, is that they have very small size limits. So you're doing metadata processing or very, very small workloads. Cloud Functions, for example, there's 2 versions, but the first version, you have a maximum of 8 gigabytes of memory to the instance. So I don't actually know anymore for Amazon Lambda how big. I don't mean to put you on the spot, Elliot, but do you know?
Yeah, I can't remember offhand, but it has, in terms of memory, I gotta say it's like, it's on the order of like kind of 816 single machine. The processing window has opened up though. Now you can run a Lambda for like 15 minutes, which is a little more useful. But I think in general, at the data sizes that we're dealing with today, you can only, even if you have 15 minutes, you got to use Lambda for what you just said, right? If there's an undeterministic amount of like, hey, this is going to be quick, it's always going to be a minute. It's not dependent on data size, right? It's not the right tool for the job, right? So even though I've got more time, I still use Lambda just for utility functions and moving things and that.
Yeah, and in Google Cloud, like functions is 9-minute timeout. So similar. The difference between functions and Cloud Run is function, you write your code and they have a limited set of offerings very similar to Lambda, like Python and Go and Node and all that kind of stuff. And then when you deploy it, they use this technology called build packs to create a container. And then when you invoke it, that container is spun up and you're charged by the invocation. Azure Functions work similarly. Cloud Run, you make your own container. So you can have any runtime then. So it's like the next level up, but it's still really, really small. But that's a big difference. So like an example we have is a lot of our people use R language for statistical analysis, and that's not available in Cloud Functions. So if we want to make these really lightweight statistical evaluations of the files, we would have to use this sort of situation here where we had a container with R language in it. So that's like at the core level. But what I've been working on currently, and I thought it's kind of relevant to talking about this chapter of transforming, is how do you scale up to apply transforms with more powerful computational primitives and services. And so this has got a lot on it here. But if you look across the verticals, if you start, like, let's just start with web apps, like the simplest web app, which is not so much a data job, but it's sort of well-known paradigm, is Cloud Run, like Python Flask and Cloud SQL, where you could have a bucket if you just had images. To scale that up, you would use Kubernetes engine. You could have GPUs. Underneath the hood, these are running on Compute Engine. And then you can use Cloud Spanner for transactions. This is probably not the data microservices example. The reason I put this here, though, is because DataMesh implements microservices, and microservices come from the operational side. And on the operational side, this is a very known pattern. And so one of the things that I see my customers trying to do on the analytics side is incorrectly saying, if this will not scale up, then what we should immediately do is we should go to this architecture, which is incorrect for analytics.
Yeah.
But it's the one that's most known. So to kind of contrast, the one that I think we're going to be really relying on quite a lot is this one right here. And the difference is that you have an invocation. So you have a function listening on a bucket for files, so an invoker. And then you use the scheduler service called batch. And all three of the big cloud vendors have this. And what this basically does is allows you to spin up and spin down compute engine. So I call it ephemeral compute.
Yeah.
And why you do this is because you can use powerful instance sizes in your nodes, and importantly, you can use GPUs. You notice over here, there's no GPUs. So for machine learning scenarios, this doesn't scale at all. You know, sometimes it won't even run. Why you would use this rather than going directly to Kubernetes is because it's simpler. You're actually using, you know, basically Linux nodes. And this is more like what was traditional analytics scaling in things like HPC or Slurm clusters. It's very conceptually similar. So if you have teams that have that kind of infrastructure, like I do, this is sort of the simplest lift to go up. Now you can use containers here, but you don't have to. You can just use scripts. And so if you've got, like, I have a lot of legacy analytics processes that are using C++, even C and Java, then you can put all those, whatever you need to put on the image. And that's a known process. So this pattern right here for kind of heavy duty legacy analytics transforms is implemented in all three cloud vendors. They all have batch, AWS batch, Azure batch, Google batch. And it's designed as a replacement for HPC on-prem. So, you know, people want to go to this one because this, I should use Kubernetes, right? And maybe Spanner, I don't really know what it does. This is what most people should start with for really heavy duty. So I'll just pause there. Does that make sense?
Yeah, a couple of things come to mind. So would you, I guess first, you know, just a question. In batch, you get like kind of that scale out capability, which I relate to like the map, right? And the map reduce, but
Yep.
but don't you also have like reduce phases that are required in some of these workloads too? And does batch support that well?
Yeah, you do. It's not MapReduce. So
I'm just thinking about it conceptually in the end, like
yeah, well, that leads
aggregate,
to
compare.
that leads to this green section right here, which is, if you notice, scaling out machine learning jobs, Python, TensorFlow, and Spark. Spark, of course, is the in-memory evolution of Hadoop, which is MapReduce, right?
Yeah.
And so if you're going to scale out Spark, then you typically will not use this architecture because you don't have all those. You'd have to write the mappers and reducers and all that. You would use Dataproc, which is managed Apache Spark. And what that basically is, it's a similar conceptually. It's a scheduler, but your nodes have Spark on them. And they have all the daemons, like they have the job scheduler and they have the blah, blah, blah. What's interesting about this, and Amazon's kind of in a similar place with EMR, Elastic MapReduce, is people are saying, okay, I want it to use containers because it's faster to scale up and scale down. And so kind of relatively recently, I would say in the past 3 years, you have with DataProc, the ability to create a cluster with VMs that you can see in size, or you can say, create me an auto-create GKE cluster because I care more about scaling up and scaling down, which for my case is not as important. This is more for like when you have to be timely, you have to be fast, like ad serving. And very interestingly, the new offering for DataProc is serverless, where you just have an endpoint. And EMR has this too, where you don't have to manage this anymore because basically you just want to have an API that you can scale up and scale down. And also notice that you can have different types of accelerators here. When Google, you have GPUs, and there are like 5 different kinds. And then TPUs, which is Google's Tensor Processing Unit chip. It's like a super GPU. It's super expensive, but it's very optimized for TensorFlow. And then even reaching out, QPUs for quantum.
Interesting.
Yeah.
So do you see this these boxes kind of as options for what's the word? The quantum. I've started using this all the time. Architectural quantums, or more just like kind of the transformation within that
Well,
box?
the way I'm seeing it is by job type, right? And so, like, if you have an example from genomics would be there's a tool kit called the Genomic Analysis Toolkit. It's a jar file, so it's Java based. And a lot of the pipelines to analyze genomic data use it because it has 150 tools in it. Like do this, do this, do this, do this, do this, do this, do this. Big old pipeline. So you would use this architecture for that. The challenge I would have is typically in the past, that has been one humongous container that was so big that actually broke Docker Hub, fun fact. And of course, it should be like 5 containers at least, right? Like the whole idea of containers is not to make VMs, it's to make containers. But they didn't kind of get the message on that. And that would support a data mesh architecture where it wouldn't just be one of these, it would be 5 of these as your data microservices. Does that make sense?
It does. I guess I wonder, those 5, would the intermediate results be like data products, or would it be more still internal?
Yeah, that's a good question.
Like, do they stand alone on their own?
Yeah. Well, it depends on where, what's the downstream analysis. The typical approach now is everything goes in the bucket and folders. It's a folder hierarchy. But that results in sprawl. It's like the change data capture of genomics. And I've had many customers like, do you read the intermediate files? No, we haven't looked at them for 5 years. Well, how about moving them to archive and save some money, right? So interestingly, about this scaling out Python, you might wonder, like, how does this work with Spark? Well, Spark has libraries, PySpark for Python and SparkR for R. Yeah. So now it's kind of a wild west right now because there's so much machine learning and the LLMs are really driving this, especially around Python. And to that end, there was something new that came out in GCP that I've been looking at actually this week. It's called Ray. And so it's called Ray on Vertex AI. And basically, the idea is you create a cluster. And in the cluster, you pick the GPU type. And then you set the disk type. Performance is SSD. And then you set the worker pools. And in the worker pools, you can set the accelerator, which is the GPU. So this is designed for scaling machine learning because you can have multiple worker pools. And then once you set this up, basically it's an open source library. The idea is for scaling AI in Python. What's interesting about this is their claim is that this is more performant for scaling TensorFlow and some of the LLM stuff than Spark. And that this is an actual problem I'm working on right now, because I am trying to figure out how to scale TensorFlow for the image analysis. And I just assumed we'd use Dataproc, but Ray has emerged on the scene. And it's kind of interesting because if you look at the example gallery, it's all machine learning, LLMs, generative AI, time series, reinforcement. And so it's written to be efficient in scaling machine learning. And then there was a paper on this that I thought was interesting. Does the underlying primitive in an array application or job is a dynamic task graph? This is very different from the computational graph in TensorFlow. Whereas in TensorFlow, a computation graph represents a neural network and is executed many times in a single app. In Ray, the task graph represents the entire application. It's executed once. So it's a dynamic. So it can parallelize more effectively. So you basically have this, LLMs are really driving transforms that use LLMs, basically, use more machine learning. And it's Spark seems like it's not the most performant. So again, I'm kind of going out there, but I have this actual problem. So, and then just to be complete, you know, for BigQuery machine learning and ETL, you have BigQuery, and then you have Dataflow, which is Apache Beam, and you have pattern like PubSub for eventing. And then in here, you have no GPUs. So you can see this would be for like the pre-processing, but at scale, like get rid of the nulls or, you know, all the sort of mundane stuff, but if you have massive, massive amounts. And then the last part in here, just to be complete, is statistical jobs. And this I haven't done as much work on, but figuring out how to scale R. The short answer is you shouldn't use R. There's a language called Julia that's designed for parallelism. The problem is if you're a researcher, you don't suddenly want to change your language.
Yeah.
You want to use R. So, so that's the problem I haven't really solved for yet. I figure I'm going to take the Python/TensorFlow case first. But I feel like these two sections right here actually have relevance going all the way back to the book of transformations. Because, you know, this again is the world that's coming, whether it's just plain old TensorFlow or whether it's LLMs. You know, how do you scale transforms where you use LLM? And that's basically, you know, TensorFlow recommender to recommend songs or LLMs. So I don't know. Again, I might be too far out there, but I'm in it. Are you guys doing anything with this stuff?
In terms of the, you know, trying to figure out this transformation layer, or specifically for
machine learning as transform.
For machine learning?
Yeah.
You know, honestly, you know, for most of my work, it's been straight out plumbing, to be honest. Although, you know, and most of the kind of like ML pipeline work I've been doing has been relatively like narrow, sane, you know, kind of traditional infrastructure. So I haven't, unlike you, I haven't had too much work in terms of trying to scale that transformation currently, but it's exciting for sure.
Yeah, we're excited about it, but we're certainly not even there. You guys are way, way, way beyond us.
Well, one of the things, Matt, that's interesting is it's going to be surprising how fast education is informed by Khan Academy. I'm a contributor, and so I get the insider thing. I was literally just on a call with them, and they were talking about the growth of Khanmigo, which is their implementation of an LLM from inside of Khan Academy as a tutor for students, and as a basically support person for teachers to help make lesson plans. And so I think it's going to be surprising how fast LLMs are going to come to education because of the influence of Khan Academy, because it's so pervasive. And also in my world, we've already got Palm Med, which is just, the hottest thing. The idea is to read and or write patient notes, which of course doctors are very, very interested in that from time saving,
Yeah.
So speaking of time, we have our all too common processing and actual time. And again, just dumping all the time. We talked about this last meeting, dumping all the timestamps in as data is an important aspect of modeling so that you can retrieve based on time windows. And she talks about that here. And this is stuff that to me is not new, but people do it wrong all the time. So I guess that's why she put it in here. And then for the recap, she talks about data products serve their domain data to a wide set of users, multimodal access, and my big addition there is egress. Egress cost estimation and egress enforcement by policy. Data products can be used in temporal analytics. If you collect the time information, is my experience there. Data products can safely consume data from other products while maintaining a global state of eventual consistency. Yeah, that's kind of aspirational. You can get a data swamp pretty easy there. But again, timestamps help a lot. And then the biggest thing that I have seen since I started reading this book is the impact of machine learning as transformation. I went from like 0 to 75% of my work in a year, which is kind of shocking,